Alright, Matthew Serber again, here with Peervids, and we are doing Chapter 5 in the Barron's book today. It's covalent compounds, formulas, and structures. So, enjoy. Alright, just a quick review. This was talked about a little bit in the last chapter, but covalent bonds, again, are bonds that are formed by sharing electrons between atoms to make molecules. And an easy way to show these bonds is with Lewis dot structures. This is I have a couple examples here. So this one here is hydrogen, and these dots show the valence electrons. Hydrogen has one electron in its outer shell, so it gets one dot. Helium has two. Helium gets two dots. Now lithium has three electrons total, but only one in its valence electron. And only one valence electron, the one in the outermost layer of its electron shells. So lithium gets one, beryllium has two, boron 3, carbon 4, nitrogen 5, oxygen 6, fluorine has 7. I think it's fluorine. Yeah, fluorine has 7, and neon has 8. So they use these dots so that then you can draw how they fit together. So for example, carbon has 4 dots. Well, then carbon can form with, I'm going to erase this dot actually. I want it down here for this. So then carbon can form with 4 other things. So let's use hydrogen for example. Now we have carbon can form with 4 hydrogens. So now you can see the hydrogen has 2 dots now with it, so its shell is full, making it stable. So each hydrogen has 2 now, and the carbon has 8. 1, 2, 3, 4, 5, 6, 7, 8. So the carbon is in a stable now because it has its full octet. So, and this molecule right here is methane. Its naming again is not important, but as you can see, the Lewis dot diagrams really help for seeing how covalent bonds work. However, when you are doing Lewis dot diagrams, you have to keep in mind that some atoms or molecules have more than one electron bond. So if I take oxygen for example, one oxygen, I'm going to do his electrons in red, has 6 electrons, and this other one, he's going to get blue. So he has 6 electrons also. Well, O2 is a common naturally occurring molecule because oxygen tends to pair up. But how are these two going to bond and each have 8? Well, they're going to double bond. So they're going to share 2 electrons instead of just the standard 1, which we saw earlier with carbon and hydrogens. So this guy on the left is going to have 1, 2, 3, 4. I want to move that over. When you draw double bonds, you tend to put them diagonally, the electrons diagonally on the sides of the oxygen to leave room for the bonds. Then this guy is going to get, because the bonds are electrons and they repel the other electrons. So instead of being on the top and the bottom like they are up here, the electrons that are now over here repel these 2 pairs backwards, so then you get them on the diagonal lines there and there. Anyways, as you can see from this picture here, the oxygen has double bonded, and now each has 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. So, and the other way you'll see a double bond drawn, I'll just do this really fast, is 2 lines and then diagonal dots. Whereas the single bond, like chlorine and chlorine, you would just get 1 line and then all the dots. So there you go. That's the first steps of Lewis dot diagram and covalent bonding. So now, if you're looking at this picture, this is two nitrogen atoms bonded together, and so you can probably see from these 3 dots, it has a triple bond. So nitrogen has 3 bonding places because when you draw it it looks like N. So it has 3 unpaired electrons. That means nitrogen can bond 3 times. Well, if one nitrogen wants to bond to another nitrogen, and they both have 3 spots, if I draw the other one here, well, what do you think is going to happen? The nitrogen's going to want to bond its electron. So that one's going to go with that one, that electron with that one, and that electron with that one. Now it's sharing 3 electrons. You get a triple bond. Boom, boom, boom. Triple bond. So that's the other way you'll see it. You'll see it written out like that. That means it has a triple bond. Where the oxygen had a double bond and chlorine has a single bond. This is again due to pairing unpaired electrons. Alright, so here I'm trying to draw the bonding process to illustrate the bonds a little better, because I realized I didn't cover a couple things in the last couple slides. So first, you have 2 oxygen molecules. So oxygen has 2 electrons in its inner layer and 6 in its outer layer. So you draw 6 dots around the oxygen atom. So that's why we have 6 dots. Now, as you can see, there are 2 pairs and 2 lone electrons. Now, these lone electrons, they're not as stable as the pairs because their orbitals aren't full. So what they tend to do is pair. So if this is step 1, down here would be step 2. One of the electrons from each one pairs. So now, as 3 pairs, this line right here, you can think of it as a pair because it's 2 electrons that are now shared in both orbitals. And then over here, however, there's still 1 unpaired electron on each atom. So that's why step 3 is right there. The second unpaired guy they are now paired. So now you have 4 pairs on each one. 1 pair, 2 pair, 3 pair, 4 pair. 1 pair, 2 pair, 3 pair, 4 pair on each oxygen. So the unpaired electrons tend to bond. Now these guys over here, the ones that don't bond, they're called lone pairs. So they're not part of the bonding process, but they do fill up the orbital, so they're called lone pairs. And these lone pairs, I'm going to go over this again, they're pushed back by these electrons in these 2 bonds. The electrons in these bonds, let's see if I could get a different color. These electrons have negative charges, and these electrons have negative charges, so they repel. And as they push apart, it pushes the lone pairs that were previously on top and on bottom, very stable, back. So now that they're at a slight angle, whereas before they were up and down, very flat. So that's an important part of drawing the pictures, is knowing where the electrons go, like at what angle. Alright, so here's a step-by-step way to look at drawing bonded molecules. So first is the skeleton. You just have all the molecules you have involved. So here we're doing methane again. We have 1 carbon and 4 hydrogens. Then you can see the bonding pairs. So we're going to go that way. It's still 4 hydrogen. Next one is just the lines. Hydrogen, 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 hydrogen. Because each line represents 2 electrons. Well, some other ways you'll see it is if I just kill this here, I clear this slide now, is you'll see like when the 2 chlorines bonded, they draw all the valence electrons in. Well, that's very good practice, but at some point it's not practical to do anymore. If you know, like 2 chlorine, they always make the stable octet with their 1, 2, 3, 4, 5, 6, 7, 8 electrons in each atom. So again, 1, 2, 3, 4, 5, 6, 7, 8. So it becomes like not practical to draw all the valence electrons. It's just extra dots and makes the paper messy. So you might just see Cl, Cl, and the 6 dots are just like implied. For example, when you see carbon, if you saw carbon bond with fluorochlorine, I would just draw it like that and not draw the 6 dots that go on every one. It's too much to do. It gets messy, and yeah, well, there you go. So I've talked about this a little bit before, but most molecules follow the stable octet rule. So they're trying to get to the same electron configuration as the nearest noble gas. So neon, for example, naturally has all 8 electrons in its outer shell. So that's why neon doesn't covalently bond hardly ever. But some molecules or atoms, they don't follow the stable octet rule. They like once you get into like the 3rd, 4th rows, you start getting some abnormalities. So phosphorus, for example, tends to bond, instead of trying to get 8 electrons around it, tries to get 10. So phosphorus will bond many times, or 10 or 12. I think it's 10, yeah. So phosphorus will start just bonding away, like they have a picture in here in the book. It's phosphorus with 5 chlorine attached. As you can see here, that makes 10 electrons in phosphorus outer shell. And for some reason, this just makes it more stable. It's complex explanation, and it's never really relevant, like, or asked about on the exam. But so phosphorus does this, sulfur does this. Just atoms in those like columns after the 3rd row just start getting messy. Iodine, that's another common one you'll see. There are more that do this, but those are the big 3 that you'll see on exams. There's phosphorus, sulfur, and iodine, and they do 10, 12, or 14 for stability instead of the normal 8, which is the octet rule. Alright, so here is another example. This is sulfur, and it's going to the 12 electron rule rather than the usual octet, which is much more common. So I did talk about this already, but just so you get an idea of what they look like when they're all bonded together, it's sulfur with the 12 electron rule. Makes it stable. Alright, so the book just wants to go over multiple covalent bonds again, so I'll just draw the carbon atom again. So as you all know, the carbon can bond 4 times. It has 4 valence electrons. When drawn like this, you can easily see that it has 4 unpaired electrons that are ready to bond. Well, if I draw 4 hydrogens that also only have 1 pair, what do you think happens? It's going to bond, 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 so they can all have, so carbon can have its stable octet, and hydrogen can have its outer layer filled, which fills at 2. So, just going to get carbon, bond, 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 bond. So, as you can see, which we already went over, the atoms can bond more than once. Yeah, there you go. However, not all the bonds have to be equal. If I have, it doesn't have to bond the same amount of times on each side. So if I have these 2 carbons, and they both are they each have the 4 unpaired electrons, and we have 2 hydrogens. Well, the hydrogens, you know how they're going to bond. They're going to bond right away, right? So now we have H, C, and it still has 3 unpaired electrons on each side. So you can probably predict that one's going to bond, that one's going to bond, that one's going to bond. So our final molecule is going to be this guy, HC triple CH, or as it is called, it's known as acetylene or ethyne. So you don't really need to know naming now still, but as you can see, the molecule does not have to bond evenly on each side. So now the book goes over drawing the Lewis structure for ions. So first you're going to draw your ion. I'm going to do ammonium, which is NH4+. So as we all know, the nitrate only has 3 bonding areas, much like phosphorus, but anyways, it only has 3 bonding areas. Well, NH4, it needs to bond 4 times with water, or not water, I'm sorry, hydrogen. So how do you get nitrogen to bond 4 times? Well, you have to get rid of one of the electrons, right? You need 4 unpaired electrons. So instead, we're going to have a nitrogen ion, where it has a positive charge. It's N+, because it's missing a one of its electrons. Lost an ion, it got a positive charge. So the next thing we're going to do is draw our 4 hydrogen. Hydrogen, 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 hydrogen. So it's going to bond, and it's going to look like exactly pretty much like the methane from earlier. Well, to show that it is an ion and has a formal charge, or a charge that is positive, all we're going to do here, we put brackets around the molecule, and then you put a plus. The plus shows the charge of the overall charge of the molecule, and it's a positive charge because it's 4 normal hydrogens and 1 nitrogen, but the nitrogen is missing an electron. Because it's missing an electron, has a positive charge. So there you go. Not too hard. Alright, so now we're going to learn how to calculate the formal charge. This is a long and complex process to do something that I don't think is super important, but it is asked on the test, and so we are going to go over it. This may take a couple of slides, and you should watch it over again if you don't get it. So I'm going to write down the steps first. 1, you're going to count the electrons that aren't used for bonding. So count the lone pairs. I'm going to use that vocab again. Alright, 2, now you're going to count half the bonded electrons. So normally each bond counts for 2 electrons. In this case, you're going to count them as 1. Alright. Step 3 is add steps 1 and 2 together. Alright, and then 4 is you're going to subtract this number. So subtract step 3 from the valence electrons that normally circle this. So I'm going to show you an example in the next slide. So formal charge. Alright, so stay tuned. So this molecule is SO4. It is a polyatomic ion, and we're going to calculate the formal charge of it. So first, we're going to calculate the formal charge of the sulfur. So we're going to count each of the bonds. 1, 2, 3, 4. And we're counting them as half this time. So we're only actually counting them as 1 each, because normally they're 2 each. And we're going to subtract that from, well, then we're going to count the lone pairs. Well, sulfur doesn't have any lone pairs in this molecule, so that's why I want to skip that step. So now we're going to take the normal valence electrons of that element. So sulfur normally has 6 electrons, and we're going to subtract the 4 bonded, and then minus 0 lone pairs, and we're going to get positive 2. Well, does that make the charge positive 2? No. Now we have to find the formal charge of each oxygen. So each oxygen normally has 6, right? Well, now 6 minus these 6 valence electrons, so 6 minus 6, and then minus 1 bond. Each one has 1 bond. So that's going to give you a charge of -1. Well, that's the charge for each oxygen. Well, there's 4 oxygens. You're going to do -1 times 4 to get -4. Now you're going to add these two formal charges together, because you just add all the formal charges of each atom involved to get the formal charge of the whole ion, or the whole molecule. So 2 minus 4, you get a charge of -2. I'm going to get rid of that little dash. So we're going to come up, well, that makes the formal charge of this -2. So we're going to come up to there, put our brackets on, and then -2. Or you'll see, if it's just written out in the molecule form, 2 minus is your charge. So, there you go. That's how you find the formal charge. And, yeah. Alright, so the next thing in our Barron's book is the resonance structure. Normally, I would have saved, actually no, I would teach this about now. So, our example is going to be SO3. Now, SO3, if I get the pen tool, SO3 tends to go, it's going to be 1 oxygen, 1 double bonded oxygen, and a third oxygen. So the sulfur has its full 8. This oxygen goes like that, and you know the bonds on this. Well, and it's also a 2 minus. That's not really important right now, but that is good practice for you to know. A real quick way for this to calculate is that the oxygen, to be have a formal charge of 0, it needs a double bond. Well, the sulfur we know has a formal charge of 0 because it has has 4 bonds. And anyways, and this is the only one, and these two oxygens will each have a -1, -1. So that's just really fast how to do it. If you have a good understanding of how to do it, I wouldn't use that quick method until you understand better. But anyways, resonance structures. A resonance structure are the other ways to draw this molecule. So I'm going to kill this now. Actually, it's a little big, so kill you. Alright, there we go. So if we have S, O, double bond O, single O, well, the double bond doesn't have to be right there. That's just how I drew it. Well, it also could look like that, right? Or it could look like this guy, where it's just down there. So that is resonance structures. That's what they are. There are other ways the molecule could be formed. Usually this is when you have a double or a triple bond that is in one place but not another, and could be in more than one place. So there you go. It's not too complicated of an idea. Just know that you can draw some molecules in more than one way, and those are called resonance structures. Alright, the book mentions a little chem briefly, so I guess I will too. So the book talks about something called, they're cyclic molecules, or cyclic alkanes, or alkenes in this case. Anyways, it is when you get a hexagon of carbon that are bonded alternatingly with double bonds. It's called a benzene ring, and it's very important in organic chemistry. Well, what's the resonance structure of this guy? It could also be this, with the double bond on top, and then single, double, whoops, that one's a single, single, double, single, and then all the H's. So anyways, that is a lot of drawing just to draw this kind of pain molecule, like a pain in the butt to do, just for something that's like, it's not that big of a difference. They're pretty much the same molecule. Well, the way they handle this, drawing the benzene ring in the resonance structure, well, they draw them both at once. So they just draw a hexagon, and it is implied that at each of these points there is a carbon. That one was not a, whoops, that was ugly. I'll fix that right now. It's implied that at each of these corners there is one of the 6 carbons. So you'll often see shapes drawn in the form instead of all the bonds drawn out. And then to show that there are alternating double bonds, they draw a circle in the middle. This counts as the resonance structure. This is just a symbol for a hexagon that, if I draw one over here, and this is what the double bonds would look like normally. Those 3 lines. Those 3 lines show that there's a double bond there, one there, and one there. Well, the circle shows that it could be like this, or it could be switched a little bit. So, could actually be like this. Sorry, my hexagons are awful, but it could actually be like that. So, the circle here is showing both of these at the same time. So I don't think the benzene ring is very important right now because you're not doing organic chemistry for at least another chapter, but it is something to start thinking about, and it is relevant to resonance structures. So there you go, benzene ring. Alright, so now the book is going to talk about electronegativity. If you remember, I drew the periodic table before in a previous video. If you didn't see it, that's fine. Electronegativity it increases across and decreases down. So fluorine is the most electronegative atom on the chart, or element on the chart, and francium is the least electronegative, which is down there, and fluorine is up there. Anyways, so that's the trends again of the electronegativity. So I'm just going to kill this guy. So electronegativity, it helps you chart polarity between atoms. So if I drew a, let's just draw a nice little H and an F. These are pretty different charges in electronegativity. You'll probably have a very detailed periodic table that'll have the symbol, electronegativity, and then atomic number, and then mass, and then so that's probably, your table will probably look something like that. If not, there might be a guide on there to show you which number is electronegativity, but it's usually just it won't ever be greater than 4, so that'll help you. It won't ever be greater than 4, and it won't be less than 0.7. So that'll help you a little bit with which number is electronegativity if you don't have a guide. So first we're going to look at our table and look at the electronegativity of hydrogen, which is the 2.2. We're going to look at fluorine. I already said it was 4. So fluorine is the more electronegative element. So you're going to draw this little guy. It's kind of a weird symbol. Looks like an 8 that didn't quite finish. And negative, so that's the fluorine. And then the hydrogen is the positive one. So to find out the electronegativity or the polarity of this atom or this molecule, you're going to subtract one electronegativity, the higher one from the lower one from the higher one, sorry, and you're going to get 1.8 in this case. So if we have our little hydrogen fluoride, we're going to draw an arrow. That's the way the electronegativity is going. It goes towards the more electronegative side. We can say it's 1.8. Now, because this number is, I believe it's like 1.5 is the barrier, so this line is, 1.5 I believe is considered the barrier, so because 1.8 is, oh that's the movement tool, whoops, because 1.8 is greater than 1.5, this molecule, don't trust me on the 1.5, I think it's 1.5, but it also might be 1, it is considered electronegative, and there you go. And then the line shows the electronegativity. So the last section that I just did was on electronegativity and polarity, so it was showing the polarity of the hydrogen fluoride. Well, now we're going to talk about dipole moments. And now, in my experience, I've never ever had to solve for the dipole moment, but it also does not appear to be a difficult formula, so I'll go over it quickly. It's also in your book, obviously, because I am teaching out of the book, so it's going to be Q, which is going to be the difference in charge times R, which is going to be the distance between two nuclei, and that's just your dipole moment right there. Q times R. So we have and the units for the dipole moment are coulomb meters. So, and the common unit for dipole moments is debye, D-E-B-Y-E. Well, I've never used this in my personal experience, and I never saw it on the AP test. And if you're only trying to prepare for the AP test, I would not bother learning it. But if your instructor specifically mentions it or tells you to learn it, then you should learn it. But personally, I don't think it's important. Alright, well, this video is getting pretty long, and we are not super close to being done with Chapter 5, so I'm going to split Chapter 5 into 2 videos, so come back and check out the other one.